the mic. But we are recording.
Oh, okay, all right. Hello, everybody. So I'm Anand Sreeram. I was a member of Cohort 1, Cunningham at the University of Nottingham. I'm an academic in the civil engineering department, so I've been there for about 2 years. This presentation is some of the work that my PhD student is working on. So it's to do with the development of digital physics-informed digital twins for asphalt pavement. So I think most of you are already aware of most of the sort of defects in roads. So the primary defect that we are looking at the moment is rutting. So rutting is basically the longitudinal surface depression within the asphalt layer. And the mechanism of that is that it's governed by sort of the densification and stress distribution in an asphalt pavement. And primarily, it goes through several stages. So there's primary rutting, secondary rutting, tertiary rutting, and so on. So from an asset management perspective, we generally try to control rutting at the primary stage, before it sort of deteriorates further. So that's the kind of deterioration mechanism that we're looking at. So in terms of what is currently done, conventional monitoring techniques, it generally fails to capture the internal stress evolution. Generally, we measure sort of, reactively, right? We measure surface defects after it has occurred. And what we need to try to do is that we need to try to get to a place where we can have proactive maintenance, and that's where this sort of study is leading towards. There's a lot of talk already, I guess, in this conference and generally in civil engineering about digital twins. So we try to bring some of that concept into pavements, which is generally, I guess, sort of a sector that does not really adopt that much of digital solutions. So how do we apply this to pavements? So generally we talk about digital twins. It's a dynamic representation of a physical asset that sort of integrates the physical model, a virtual model which has sort of sensor inputs and also other relevant information that kind of mirrors the life cycle of the asset. So this is generally how we could do something like this for pavements, but in terms of pavement digital twins, there are a number of different challenges. Development of a digital twin requires data from a virtual model, things like sensors. And really, when we talk about pavement digital twins, generally we've been using things like BIM, right? So they are two-dimensional representation of an asset, but deterioration in a pavement is it's a material-based concept. So we need to capture that material deterioration in the virtual model, and that's where this study sort of looks at that. So in terms of the research gaps, we're looking at understanding the challenges in capturing the internal material scale behavior, because that's what really leads to pavement deterioration. We have a number of existing virtual models, but they don't really capture the physics of deterioration, right? So how do you bring the physics of deterioration into virtual models, and how do we integrate, different kinds of measurements from sensors, from other data sources into these virtual models, and that's what we're trying to do. So initially, we tried to use sensors that can sort of capture the real-time sort of deterioration as well as the internal physics of that, and putting that data into a virtual model which has the exact physics, right? So most of the virtual models don't have this physics, so we use something like what we call as the physics engines. So these are sort of available softwares, but it has to be kind of designed for asphalt pavements. In terms of coupling that, we looked at something like using sort of wireless sensors. So these have morphology similar to real aggregates. They transmit data using technologies such as Bluetooth technology and so on. And the real sort of the challenge is to develop computational models that are less computationally intensive, right? Because most of the FEM, DEM sort of techniques are very computationally intensive. So we used something called physics engines. These were originally developed for computer games, and they can be now used to simulate the behavior of granular materials, things like soils and clay and so on. So we use that same concept in pavements. So our main objective was to develop a computational framework to develop for a physics-informed digital twin to replicate primary rutting by linking the sort of the internal asphalt pavement response with external deformation. That was the main topic that this research focused on. So how do we do that? Yeah, so we tried to fabricate specimens in the lab with different gradations and so on, but it had something called a smart rock, which would give the information from the pavement for us to integrate into the virtual model. In terms of the virtual model, yeah, we looked at developing the virtual model. I think this is the sort of the very difficult task because essentially we want to capture the real pavement in a virtual environment. So that includes us, that we would have to include several sort of physical processes, things like bonding forces, damping forces, and so on. So that's where the real challenge lied. Yeah, and then we had to validate the model. So we looked at things like the compaction characteristics, how that height varies in the virtual model. Can we sort of correlate what's happening in the physical model with the virtual model? So yeah, that's something that we did. How much time do I have? Sorry.
You have 4 more minutes.
Okay. Right. So yeah, so I don't want to go into depth. So this is what we basically tried to do. So we looked at comparing the compaction characteristics with the physical slab. So one of the main things we looked at was density. So density is an internal state variable that directly reflects the structural evolution during compaction. So we looked at understanding the different trends in the virtual slab and also the compacted slab. Yeah, so this was mainly looking at the real-time response during compaction. So we looked at how the smart rock information can be used to understand the different sort of aggregate interlock mechanisms and progressive densification and so on. And essentially, we're trying to replicate exactly what happens in a physical slab in the virtual slab. So that's what this work was trying to do. So how do we take this forward? So our main sort of idea now is to develop a sort of virtual lab. So instead of doing a physical test, we could replicate all of that in a virtual environment. So we have in terms of asphalt pavements, we generally simulate rutting using what we call the Hamburg wheel tracking device. So we can now simulate that. Sorry, could I have some water, please? Yeah, so now we can simulate that using a virtual model. So we have a Hamburg wheel tracking test. So this is how a wheel tracking test generally runs. So now we can simulate that in a virtual model, and that's how this study is proceeding at the moment. And then, yeah, we're basically, we're trying to improve our model, trying to, use different sort of gradations, different types of binder, different testing conditions, and we're trying to simulate all of that in a virtual environment. And this is some of the data in terms of, in terms of correlating the model and calibrating the model. So we're looking at, can we, can our physical test and our virtual test exactly sort of replicate? Are the mechanisms of damage that occur in the virtual model exactly the same as the physical model, and so on? So yeah, I think this is quite a promising sort of area at the moment. So this is the overall sort of framework that we are looking to move. So instead of doing all these sort of tests in the lab, we can now move to maybe a virtual environment where we can replicate exactly the physics of these tests in a virtual environment. So, I mean, it's not great news for the equipment manufacturers, but I think there is a potential that we can maybe, instead of having these large laboratory spaces, we can use more digital tools to at least simplify some of that process. Yeah. So just an overview. I know it's very technical, but yeah. So just hopefully that gives an idea of what we're doing. Thank you.